My name is Eric Laliberté. I'm the Director General of Space Utilization Branch at the Canadian Space Agency, but more importantly, I will be the moderator for this session. So on behalf of the Earth Observation Committee of the International Astronautical Federation, I am pleased to welcome you to this one-hour plenary event on the theme, the Cryosphere in Retreat. When I was first approached to be the moderator here, I said, cool, we can lower the temperature of the room, we can have ice sculptures, snow coming in, and maybe even artificial ice and skaters, and then we said, no, that's going to detract from the subject. So instead, we challenged three distinguished guests, three people that can be on and by themselves, each a keynote and address this topic at length. And we've challenged them to be a tag team on the subject of the cryosphere. So the cryosphere includes a portion of the Earth's surface where water is in solid form. Sea ice, lake and river ice, snow cover, glaciers, ice cap, even frozen ground. You can think that Canada has a lot of that. The cryosphere is a fundamental element of the global climate system that influence large-scale fluxes of energy, moisture, and gases. A significant fraction of the cryosphere, mostly in the northern hemisphere, is close to melting and is therefore very sensitive to temperature changes. The cryosphere seems to be retreating on many fronts, which may lead to large shifts in the climate system. So even if the main elements of the cryosphere are far away from most of us, the effects of a retreating cryosphere may have global impacts. I would like to thank our three panelists who accepted to present and discuss on this topic of great importance. But before I introduce them, I have a little bit of logistics. So for questions, if you have questions throughout, I invite you to raise your hand. There's personnel in the room that will give you a little piece of paper so that you can write the question. And then there will be a couple of individuals that are sitting right at the front that will bring those questions and make sure they get to me. I think green. Oh, you want the slides? Thank you. So, introducing our three panelists. Professor Andrew Shepard from University of Leeds, who is Director of the Center for Polar Observation and Modeling and Principal Scientific Advisor for ESA's Cryosat mission, will first present the latest data on the cryosphere. Professor Paul Kushner from University of Toronto, who is a Principal Investigator for the Canadian Sea Ice and Snow Evolution Network, will report on the predicted evolution of the cryosphere in the next 50 to 100 years. Finally, Dr. Martin Fortier from Université Laval, who is the Executive Director of the Arctic Network of Centers of Excellence, will discuss the human impact of a retreating cryosphere. So without further ado, Dr. Shepard, the floor is yours.
Thank you. Good morning, everybody. I'm very pleased to be able to speak here today about recent observations of the cryosphere that we've collected using satellites. It's only 8 minutes, and that's not normally the amount of time you would devote to this topic. So anybody that has any questions, I'm very happy to sit around afterwards and answer any other questions. So it'll be a quick skim through of the things that we've found out over the past 10 or 20 years. Most of my work is with ESA missions. I'm Principal Scientific Advisor to the Cryosat mission, which is one of only 2 dedicated satellites to look at the polar regions. But we've managed to use a lot of other satellites which were not designed for this application over the past 10 or 20 years to great effect. So the polar regions, this is a brief introduction to what they are and where they are really most often divided into 3 different areas. There's the polar ice sheets of Antarctica and Greenland, and they contain the most water above sea level. They could pose a threat to sea level rise. There's the sea ice cover in the northern and southern hemisphere, which is important because of its interaction with the climate system and its potential to change the planetary albedo. And then there are mountain glaciers, which are almost everywhere on the planet and are, in addition to their reserve for sea level rise as they melt, they're an important hydrological resource. And I'll talk about all three sections of the cryosphere and what we know about them thanks to satellite observations. But just to emphasize the point of why we need satellites, this is a UK-centric animation, I apologize. The polar ice sheets in particular are very large, and so if you look at that for scale, it's not likely that one can survey the changes with any certainty by just taking field observations or even aircraft observations. Although it is true that we rely to a large extent upon ground and aircraft observations to improve our understanding of the satellite measurements, and that continues to be the case. Very, very brief introduction to the main satellite techniques that we use to look at the polar regions. Satellite altimetry, which is first designed to look at the global oceans and changes in ocean currents and sea level rise and sea surface wave heights and wind fields, has been actually a really powerful tool for looking at the polar ice sheets. We can measure changes in their shape over time, and that gives us an idea about how much ice is stored in them or how much ice is, in fact, being lost in different areas. INSAR, interferometric synthetic aperture radar, is a technique we use to measure the speed of ice. We also use it to measure the speed of Earth deformation in other areas of the planet. But the speed of ice tells us a lot, because if the ice is evacuated more quickly than it ought to be from the polar ice sheets, then sea levels will rise, and the converse is also true. And more recently, although now this is an old mission class as well now, it's 10 or 12 years old, we've had satellite gravimetry, which weighs the Earth beneath the orbiting satellites and tells us about mass transport in the climate system, whether there are changes in mass on different locations of the planet, is important because those locations could be a store of water. So the polar ice sheets, what do we know about them? Well, this is a beautiful picture of Greenland, actually taken from the space shuttle. And you can see that Greenland, even from this altitude, 200 kilometers, is characterized by these very, very long, narrow fjords. It's an ice cap that rests on land above sea level mainly, and it's drained by fast-flowing outlet glaciers. But they're really challenging for satellites because these fjords are very long, but also very narrow. So the glaciers themselves may be somewhere between 1 and 5 or 10 kilometers at the largest wide, and we need powerful sensors to look at them. And the instruments that we've had in the past to look at the ocean were just not well suited to doing this. And so things have moved on very rapidly over the past 10 years or so when we've had better quality data to look at it. But we're, of course, interested in changes in the ice, in the polar ice sheets, primarily because of their contribution to global sea level rise and their potential future contribution to global sea level rise. And this is important because before we had satellites to look at the polar regions, most people understood them to be very, very slowly changing beasts that didn't affect sea level rise. We now know that that's just not the case. Jakobshavn-Isberg Glacier in Greenland is now flowing at about 17 kilometers per year. You can sit and watch it move meters in hours. It's the fastest glacier on Earth. 10 years ago, it was flowing at 5 kilometers a year. It's tripled its speed. And this is important because it tells us that the ice sheets are very dynamically active and can change quite quickly. And that behavior needs to be incorporated into the models that we use to predict future sea level rise, and right now it is not. The most important thing that we've found about the polar ice sheets over the past 20 years, I would say, is we now know the amount of ice that's been lost from them. You might think that this is a very simple thing to understand, but it hasn't been. So on the bottom of this slide, it's a busy slide, I apologize. On the bottom of this slide shows the satellite missions that we've used belonging to various space agencies over the past 20 years or so to measure changes in the mass of ice in the polar ice sheets. We've used more than a dozen different satellites. All but 2 were not designed to look at the polar ice sheets, and that just shows you something of the ingenuity that scientists have created to measure the cryosphere today. What do we know? We know now that the polar ice sheets themselves have contributed about 11 millimeters to global sea levels over the past 20 years, which is not a lot. I mean, it's this much spread around the whole of the polar oceans. Antarctica is the smaller contributor, about 3.7 millimeters since 1992. Greenland, about double that amount, 7.4 millimeters since 1992. And altogether, as I said, 11 millimeters. Not a lot, but actually something of a concern. More because of the way the contribution has changed over time. So if you look at in the 1990s, the polar ice sheets were about 0.3 millimeters per year of global sea level rise, about 1/10 of the sea level budget. And today, in fact, it's worse than this. This is data from 2005 to 2010. More recent data shows an additional increase, and you'll see that in a moment. The ice sheets are 1 millimeter per year, a third of the global sea level budget. So their contribution to sea level rise is on the up. And as you can look at those curves, and it's not changing. So if you were a financial investor and you were looking at these share prices, you'd probably be very pleased about the rate of growth of that investment. And so we should equally be concerned about the rate of loss of ice. This is the classic data that we would have used in the past. This is data elevation changes of Antarctica from ocean altimeter missions. And you can see that they're ocean altimeter missions mainly because there's a big missing area in the middle of the ice sheets. We can't see that pole hole in the northern and southern hemisphere because the satellites were designed to look at the global oceans and not the polar regions. It's a big emission area, but it's not as big as the emission at the coastal areas of the ice sheets, which you can't see here because it's a 5-kilometer strip that circumferences the whole of the ice sheets where we don't get any measurements because the coast is too steep. And so when we look at changes in elevation, which we convert to changes in mass, we're missing a lot of the story. And so this is how we now see the polar ice sheets. This is data from Cryosat, the first altimeter mission to be designed to look at the polar regions. It can see very much closer towards the pole, but more importantly, very, very fine spatial resolution. And we find that, in fact, we made a mistake. Antarctica is losing twice as much ice as we thought it was when we looked at the ocean altimeter data. And that's an important point because we can use missions that are not designed to look at the cryosphere to some effect, but what we can't do is characterize what's happening in the areas that you're not looking at. It's not easy to do that. Mountain glaciers, most people will know that they're in a state of retreat. This is Bear Glacier in Alaska. You can see that this glacier has changed its shape. It used to occupy this Piedmont lobe 100 years ago, and it's retreated by about 25 kilometers in the last century. It looks very beautiful, but it's actually telling us an important story. In addition to their contribution to global sea level rise, mountain glaciers are actually a water resource for many people on the planet. And the rate at which they're melting is very important because people need to have some confidence in when they're going to irrigate their crops. And it matters that the melting season is changing as a function of time and the water is delivered at a different time of year, and in fact more so for future forward planning. So it's not just a concern for sea level rise. Mountain glaciers are in fact right now still expected to be half of the mass contribution to the global oceans over the next century, just because they're distributed in warmer parts of the planet than the polar ice sheets. But their hydrological impact is also important. Over the past few years now, maybe 10 years at the most, we've managed to assemble the most complete inventory of the planet's glaciers. There are about 170 to 200,000 glaciers on Earth. It's a large undertaking, but that's now been completed. This plot just shows the distribution of those glaciers around the planet in yellow, and in the circles that are stamped on top of it, it's the amount of ice that's being lost. So the amount of ice is proportional to the radius of that circle. So you can see that there's large ice losses, in fact, in most areas of the planet where we have mountain glaciers today. And it's important to be able to characterize where these glaciers are so that we can try and model what's going to happen to them in the future. But it's also important to characterize where they are when they're close to the polar ice sheets, because some of the satellite techniques we have, like gravimetry, can't resolve or distinguish between the mountain glaciers that are around the polar ice sheets. This is just a map of those around Greenland, and the ice sheet main itself. So in the past, we were double accounting the amount of sea level rise from mountain glaciers that are peripheral to the ice sheets. We can now separate them out, and this plot just illustrates that. And the final thing I want to talk about is the Arctic sea ice. This is a beautiful photograph taken from the Polarstern. It's the Alfred Wegener Institute measuring the thickness of sea ice in the middle of winter in a very inhospitable environment. But we need people to do this because the satellite techniques that we rely on to tell people the bigger picture, what's happening across the whole of the polar region, are uncertain because we really don't know how much snow is deposited on top of the sea ice itself. We can't use just weather prediction models because the sea ice is mobile. You'll see that in a moment. And the snow gets advected around. And so it's a more complicated problem than just looking at patterns of snowfall. So we rely heavily on people to make these measurements. And it's a dangerous task, particularly when the sea ice is getting thinner and thinner. And so all credit to people who do this. This is just a nice animation of the Arctic sea ice cap. And you can see that it's not like the polar ice sheets. It travels around. It moves around with the winds and the waves and the ocean currents. And you can imagine, for sake of argument, that the Arctic sea ice cap rotates once per year, something like that. And it's obvious then, if you want to calculate the volume or mass of Arctic sea ice, you need to look at the entire Arctic region, because the ice, this is just masked out now, the area of the Arctic region that's not observed by the ocean altimeters, and the ice could be moving into that location. So if you're not sampling the whole of the Arctic, you can't ever tell anybody whether or not the amount of ice stored in the Arctic is changing. And so we now have Cryosat, which does look at the whole of the Arctic region, and it can look at the big picture, the full story of how much ice is moving around everywhere in the Arctic. And you can see that lots of ice does get transported into this pole hole at different times of the year. What can we do with that information? Well, we can make the first estimates of the volume of Arctic sea ice, the complete Arctic sea ice pack, without making wild extrapolations. 60% of the Arctic sea ice was in that location, that pole hole. And so measuring the 30% around the edges is not ideal, suboptimal, you might say, but it gets worse over time, because if the Arctic sea ice is shrinking as a function of time, then we're measuring less and less than that. So we need these polar missions that are able to look at the polar regions, not just the global oceans. And over time, Cryosat shows us in the yellow data that the best models that we have of Arctic sea ice change, which is this constant curve here, are underestimating the rate of growth of sea ice as a function of time. So that needs to be tuned. There's some missing physics probably in those models. We can see that actually over the first 3 years of Cryosat, the Arctic sea ice volume reduced steadily, which is a picture that people are very familiar with. Reducing area and volume of Arctic sea ice over the past 20 years is a very familiar news story. And it reduced steadily in winter and also in summer by about the same amount, 400 cubic kilometers per year. But this last year, we've seen the influence of anomalous weather patterns. A relatively mild, by mild I mean cool, Arctic summer in 2013 allowed ice to live longer into the next season, and now the ice has recovered somewhat. And in fact, the recovery of the past year in volume, which is the important aspect of the sea ice in terms of the energy balance in the Arctic region, has outstripped all of those losses. And it's important to be able to monitor these changes, but also to place them in the context of long and short-term variability. This is a clear short-term weather event which is going to take us back and give us some sort of reprieve at the rate of which sea ice in the polar region is lost. But it'll only be a 2 or 3 year reprieve. That amount of ice will be stripped out again and will continue to decline into the future. So just to finish and summarize what I've talked about, this is a nice front cover from the New York Times earlier this year, and it was a really nice example of the media using satellite measurements, because all of what I've just talked about just then appears in this illustration. So the first plot here, if you can squeeze and squint your eyes, is that sea level curve. The ice sheets are up from 10% of global sea level rise to 30%. This is this nice map of Antarctica, the first complete picture of changes in Antarctica from Cryosat. Shows that ice losses are double what we had thought they were based upon these ocean altimeters. The Randolph Glacier inventory has been completed. The first benchmark baseline data set for 200,000 glaciers on the planet, and first complete survey of the Arctic sea ice region. The Antarctic sea ice is a more challenging environment, and that's a story for another date. So I want to finish there. Thank you very much for your time.
Good morning. My name is Paul Kushner. I'm a professor in the physics department at the University of Toronto, and I really appreciate this chance to talk to you today about the future of the cryosphere that Andrew has given us a very nice overview as to its present state. I'm speaking on behalf of a research network called CANSICE, a Canadian Sea Ice and Snow Evolution Network. I'm the PI of that network, and we do a lot of work in the area of modeling and forecasting of snow and sea ice variability and change. So I'm going to talk to you about three basic points. First of all, that the tools we use to forecast the future, these climate models where we try to attempt to bring all of climate together into a computer simulation and use that both to understand and predict what will happen in the future. These tools have improved vastly over the last few decades and have become very powerful. A graphic that shows this is shown here, and as you go from left to right and then down the page, you see that with each generation of model, starting from the 1970s in the upper left and going down to the more recent assessments, the AR4 and AR5 assessments, we progressively add more and more sophistication and realism to these models, adding more interactions between the cryosphere, the atmosphere, the oceans, the biosphere, in a way that allows us to ask questions we never could envision several decades ago. At the same time that we're adding all this sophistication to the models, we're also increasing their resolution. So we're resolving more finer and finer scales, which particularly for the cryosphere, as Andrew mentioned, is particularly important as we're trying to understand interactions between weather systems and cryospheric components. And all this effort to make the models better has paid off. This is a graphic from a paper in 2008 showing the previous generations, 1, 2, and 3, of climate simulations. And as you move to the left in this graph, it indicates that the models are improving relative to observations. And each of the dots on each of the horizontal lines indicates the contribution from a different modeling center, typically a nation's modeling center that has put together one of these models. You can see that there are a large number of models, and that as a whole, in the aggregate, they've improved considerably by this measure. So the standards get tougher, and the models are meeting those standards. So having some sense of the tools, and I'd be happy to talk to any of you briefly or at length after the talk, we can talk about how we use them in particular for this forecasting exercise. How can we use them to tell the future of the cryosphere? We can use them in two basic ways, on shorter time scales from, say, a few years to a couple of decades. We can try to run them from realistic initial states of the ocean and cryosphere. And then we can also project far into the future over the next several decades to 100 years. And this is what I'll focus on in the next slide. I would say that because of the forcing that we're talking about is very strong from greenhouse gases, that there's more certainty about the next 100 years, ironically, than there will be about the next 5 to 10 or 20 years. So just to set the stage, the top graphic here shows a figure from the IPCC fifth assessment report. And in red is the global temperature response. You can see in degrees Celsius going from 1950 up to 2005 and then forward to 2100. And you can see an increase in temperature of about 4 degrees to the end of century. This is global temperature under the current trajectory of climate forcing, and that's shown in red. And the envelope of curves, about the central line there, indicates a measure of the spread among models. The blue curve in that same panel on the top shows the result of the response to a climate stabilization scenario. So there's warming of about 1.5 degrees or so, but it's not as severe as in the case of the strong driving scenario. Now, the cryosphere goes along with temperature to a large extent. So as the Earth warms, the cryosphere retreats. And we see this particularly strongly in the extent of Northern Hemisphere sea ice in September, which is the time of the sea ice minimum in the Arctic. And this family of red curves that indicate the strong warming scenario show that we will have an ice-free Arctic in the range of 2040 to 2060, according to these models. And this particular graphic is interesting because the models that have been selected to highlight are the ones that best represent the climate of the 20th century. And this is where we are now in the state of the art, where we can actually identify models that do better and use them, have more confidence in them to forecast the future. Under climate stabilization, we certainly get sea ice reduction, but not this dramatic sea ice loss. Along with the sea ice go many other cryospheric variables. So I'll just highlight a couple of others. We see that permafrost, which Martin is going to talk about next, is a very temperature-sensitive variable, and we see dramatic reductions in permafrost to about 2 million square kilometers from its current values of roughly 15. And that is a huge loss, of course, going to the end of the century. And then the other scenarios show a range of possibilities. And I would say much of our uncertainty really relates to how strongly we will force climate in the future. The snow cover, which is another important part of the cryosphere, certainly here in Canada, is also quite sensitive to temperature. And particularly what I'm showing here is June snow cover. In red is an observational estimate from satellite observations. And in black is a family of curves from climate models. All the variables here have been standardized in a way. So basically what you're looking at is a percentage change, and we can see that particularly in Eurasia, but also in North America, we're seeing a very great loss of seasonal snow cover in summer and also in spring, not shown here. And glacial retreat has also been mentioned, and I'd just like to highlight that this is projected to continue. The models here aren't as comprehensive, aren't as exact. There's a lot of process-based models, but they use the climate models as input. And this, also taken from the IPCC assessment, shows the contributions from both thermal expansion to sea level rise, but also the glacial and ice sheet contributions in the purple and green and blue confidence intervals there. And what you can see is that there's a lot of uncertainty in these parameters, talking about 60 centimeters of sea level rise by the end of the century, and you can see a wide range. But overall, the cryosphere is a big contributor to this going forward. So I've shown you a lot of data, some somber graphs, and you see that there's a lot of imprecision. By imprecision, I mean those error bars, which I think are always an important part of science, to talk about uncertainty. So while we're faced with this uncertainty, how much of it is intrinsic and how much can we control or account for, or if possible, reduce? Because a precise forecast is certainly a more useful one. In trying to do this is where most of our research investment is going now, and Earth observations from space or ground-based sites are absolutely critical in this. And I speak of this as a modeler and not as an observationalist. We absolutely need these space-based observations. This graphic shows how we've been trying to quantify different sources of uncertainty. The orange curve there shows uncertainty arising from internal variability, chaotic variability of climate. The blue curve shows how much the models disagree with each other. And the green shows our key uncertainty in the far future is really how strongly we'll drive the climate system. And all these different sources of uncertainty, indicated by the relative widths of the envelopes, all indicate that there's a time dependence to all these uncertainties that we need to account for when making forecasts. We have a real need for measuring those hard to obtain variables like sea ice thickness. This shows kind of the state of the art. Christian Haas provided me with this graph showing the few measurements of sea ice thickness that we have, which are now increasing, but going back to the 1970s, we have the submarine data, we have airborne measurements, we have satellite-based measurements, but this is such a critical parameter that everything we can do to maintain a climate monitoring record going forward is going to be critical to controlling our forecasts in the future. In our own network, we focus a lot on snow as well as sea ice, and we do a lot of process model studies. And this shows the way we look at different satellite estimates, which often disagree. There's two black curves that disagree about the amount. Albedo changes, the brightness of snow changes as you go through the seasonal cycle. And we have a couple of curves from models there, both land surface models and coupled climate models. And it shows that there's a lot of work in just bringing the models and observations onto an even footing. A real test of how the models perform is to use them as true predictors, and this is being done by Environment Canada. And this graphic shows in the red the impact of introducing realistic ocean observations into a sea ice forecasting system. Relative to the blue curve, we see there's an improvement in skill. So just to recap, the main message, of course, is that the stage is set for a profound retreat of the cryosphere in response to global warming. That I can state with a very high degree of certainty. What I wanted to tell you about some of the background is that the tools we use are getting better, and we're always challenged to improve them to reduce the uncertainty of the forecast. And in all this effort, we really need improved observations from all quarters, certainly from space-based and also ground-based observations of the cryosphere. Thank you.
Just as Martin is getting ready to talk to us about the human impact, just a reminder that for questions, please attract the attention of the personnel that is roaming the room, and make sure that the questions come to me. So go ahead, Martin.
Thanks, Eric. Well, thank you for showing up this early in the morning. I'll be the last speaker of this panel, and hopefully we'll have time for session. We've been going a bit over our 8-minute mark, and I probably will do the same. So my name is Martin Fortier. I'm the Executive Director of ArcticNet, and I'm here really to represent this network. It's a large network in Canada, represents about 150 scientists and 1,000 students and staff in 35 universities across the country. So working very closely actually with humans in the Arctic, mostly Inuit in our case in northern Canada, but also other stakeholders such as industries and governments. So I guess we've already seen from Andrew's talk the major, and you can imagine the major impact that these large changes in the northern hemisphere, but also in mountainous areas around the world and also in Antarctica will have on humans. For today's talk, I'll mostly focus on the Canadian Arctic, but many of these consequences can be seen also across the world. So we've worked on obviously on adaptation issues in Canada with climate change, and especially actually for about 10 years now more, focusing on northern communities in the north of Canada. North of Canada is 40% of our country, but only holds about 100,000 people. So it's one of the sparsest population on Earth, but still numerous communities and that have been there for a long time and that are suffering a lot of the consequences, the early consequences of climate change. And we've done also reports more regionally now, trying to downscale some of those predictions and also working closer with communities to try to look at adaptation measures potentially in the future. But on the circumpolar world, maybe the latest and most comprehensive assessment is an Arctic Council AMAP assessment called SWIPA for snow, water, ice, and permafrost in the Arctic. And if you're interested in this topic, actually I strongly encourage you to look at this. It's now being updated with the latest numbers and it will be out soon. And it's now being integrated in this the next Arctic Council assessment actually called Adaptation Actions for a Changing Arctic, where we are going to try to regionalize, if you want, some of the issues and some of the adaptation actions and recommendations for government facing rapid changes in the Arctic. So some of the impacts, and a lot of this is out of the SWIPA report, obviously when you talk about humans and the North and Northerners, a lot of them, whether in small communities or in larger sub-countries like Greenland, really depend on the Arctic ecosystem for the economy, subsistence, culture. And there are major changes in the cryosphere, whether on the sea ice or on land, that have a large impact on habitat and ecosystems in the north. And indirectly will have an impact on humans, whether, like you see here, Inuit in Tuktoyaktuk harvesting beluga for muktuk, which is still a very important source of cultural but also diet source for them, but also in Greenland, where 90% of Greenland's economy is based on fishery and 50% of that on shrimp fishery. That is also reacting quickly to changes in the North Atlantic. So the Arctic cod, sorry, I see the Arctic cod there. It's a staple of the Arctic food chain, but the food chain in the Arctic is extremely specialized. Low diversity, but it's very specific and very specialized. And the higher you go in the Arctic, the more dependent on sea ice it is, whether it's dependence on the ice algal bloom, but also the timing of sea ice retreat and formation in the fall will really influence the timing of the plankton bloom and the entire transfer of energy. Most Arctic animals are very fatty, but they have a very slow growth season to get and accumulate this fat. And this is a paper from last week or 2 weeks ago in JRL showing, using SAR and ocean color remote sensing, that over the last decades, there's been a shift basically in a new appearance of a fall plankton bloom. So normally in the Arctic, we have this sort of high, large spring plankton bloom, but now with the opening and prolongation of the open water season, increasing storm activity in the fall, we are seeing mixing and a fall bloom, which is more typical of southern ecosystem, and that certainly has an impact on ecosystem shifts and species. There are also obviously very direct impacts in the communities directly. In Arctic Canada here, about 50 of the 52 Inuit communities are directly on the coast, and they have a very strong connection with the ocean and the sea ice, but also they are very vulnerable to coastal retreat and permafrost changes. So you can see here, this is permafrost. If you've never seen permafrost, it can go down hundreds of meters, but especially in the coast where sea ice is receding and we have these increasing in storms, we're seeing more and more permafrost degradation and coastal erosion. And this has direct impact in some communities, like this is Tuktoyaktuk. So this is there's soon going to be a road all the way there if you want to drive there to the Arctic Ocean. So this is the northernmost community in the Western Arctic and very, very exposed to the ocean and coastal erosion. So this is a street. It's not in Quebec. It's actually in the Arctic. But Arctic infrastructure is extremely influenced, obviously, by permafrost. A lot of the infrastructure, a few decades ago, permafrost, it says the word permanent in permafrost. And I guess engineers thought it would be a permanent structure to hold some of these roads and airports and buildings, and it's not the case. And in some regions, there's major damages to infrastructure. So with some of the research and working closely with the communities, traditional knowledge, remote sensing, so merging the entire spectra of technology and information, we're now building these community plans to try to inform them as they expand, because most communities in the north are expanding, where to build and where not to build. So we're building these maps, if you want, of hazard maps where communities can expand. Major work is now being done on some largest airports in the Arctic, like Iqaluit, that are suffering from permafrost issues. One of the, maybe the aspect that's probably the most news-worthy and in the news a lot is the increased transport and access to resources, whether it's mining, oil and gas. The Arctic, as you know, holds a huge amount of these resources. And with decreasing ice cover, easier access, whether it's tourism or shipping, we are seeing an increase in activity in the north. And that has impact either locally, but also globally on the global economy. So again, locally, numerous hunters now are doing more and more risks, more drownings, much more difficult for them to predict and use traditional routes that they've been using for decades. So we are now working with communities to install sensors, using remote sensing also and data integration to try to inform them, if you want, on the safety of some of the travel routes or alternate travel routes to access the land. On a broader scale also, Andrew mentioned increase in glacier flow in Greenland, but also ice shelves in northern Canada. We're losing a huge amount of ice shelves and large glaciers. This is a Petermann Ice Glacier fragment, and this is actually a small, very small portion of Petermann Ice Island. And you can see, I hope, the Amundsen icebreaker besides it. It's a 100-meter ship, so that's about a kilometer and a half, 200 meters deep. So these are potentially unmanageable ice features that are showing up more and more. And there are oil rigs downstream in the Beaufort Sea, plans to drill also, and these are very important aspects that we need to try to deal with when dealing about potential oil and gas or shipping. More open water equals more traffic. Also, you've seen increase in traffic, whether it's the North and Eastern Sea route, but also North Passage and other areas where tourism is increasing. And this, in 2010, we had 3 groundings of vessels in the Arctic, Canadian Arctic. Luckily, no spill or no major, incidents. But there were some close calls, and things could have been much worse than they were. And you can see here this sort of underwater cliff that the Clipper Adventure hit. There's lots of those, and only 10% of Canadian Arctic is actually mapped to modern standards. So a lot of work to be doing that. Just to put that maybe more on news, this is last week, and actually today you could add a little red dot there to the west. The MV Nunavik officially crossed the Northwest Passage, so I think this morning entered the Bering Strait. And this was, again, the first unescorted transit, the bulk carrier. This is owned by FedNav in Montreal, and these are major 190-meter long bulk carrier, very strong icebreaker, but it was unescorted, just crossed the Northwest Passage, taking some nickel from a Chinese-owned mine in Quebec back to China directly to the Northwest Passage. So that's something that will continue to go. Also in the news, I guess 3 or 4 days ago, Russia and ExxonMobil and Rosneft hit this mega oil field in the Kara Sea, 1 billion barrels of oil, potentially more than the U.S. part of the Gulf of Mexico. Again, a huge impact, and one of the reasons these new fields are being exploited is the economic benefit is derived on ice conditions, open water season, and that's a very big part now with geopolitics involved, and now they're going to exploit that oil field. So, and obviously focusing on the north, but as Andrew said, and I'm going to close on this, I know we're a bit out of time, but there are global consequences to these changes, whether it's climate patterns, worldwide climate patterns, but also global sea level rise. And this is a sort of an alarming picture, but it's still, everything you see in red here would be flooded if we had a rise of 6 meters of the water. And whether it's 1 meter or 4 meters, there's going to be a huge impact of this seawater rise. As you can see, most of the red coastal area, if you look at the U.S. and you have a cabin, or in Florida, it's underwater, in New York's underwater. So maybe that's going to be a thing that will get governments moving, because a lot of rich people are going to lose their house, may just move up. But it has a major impact, but also on very vulnerable communities like the northern areas of our country. I'll leave it up there for questions. Thank you.
Thank you very much to the three of you. And I'd like to invite a round of applause for our three distinguished speakers. So and thank you, I just got a few questions, but just to start things off, I know we have here a Congress that people, and going back to the opening ceremony, we have the entrepreneur type, we have the government official type, we have, of course, the scientific type. But really, the question, I think to you, the first question would be, we've seen how much data we need in terms of monitoring and of predicting and analyzing the impact. So, do we have all the tools we need, or what would be basically additional tools or additional means that we would need in terms of helping your job and helping the society as a whole?
I can answer that. We've used, I showed in my presentation that we've used missions that were not designed to look at the polar regions to some success over the past 10, 20 years. But as soon as we got a mission, Cryosat, and ISAT, in fact, which flew for some time, about 10 years ago, that was specifically designed to do this, we realized that there were lots of things that were missing. And in fact, there's no continuity, there's no follow-on mission for Cryosat into the future, and there's going to be a large gap, and there currently is a gap in our capability to map ice velocity from space as well, the speed of ice. We don't have synthetic aperture radars. So we do need the people in charge of budgets to consider the importance of satellite measurements going on into the future and long-term records. And of course, I also mentioned that satellites are not enough on their own. And a lot of money gets spent on satellite missions, and not so much money gets spent on the hard work of collecting measurements on the ground. And those long-term monitoring stations that we've relied on quite heavily are very, very few and far between. About 50 glaciers on planet Earth of 200,000 have long-term records of how they've been changing, and that's just not adequate. And we need people to spend extra resources to look at those parts of the planet too.
Thank you. I have another question here. It says, from an economic perspective, would it not be better for Canada, or we can extend that to Arctic countries, if the North Polar ice cap melts completely, so that our ships could have direct access to Asian markets?
I mean, I'll comment, but everyone else will have a view. It's important to acknowledge that there are economic benefits to a changing climate as well as societal impacts. From my perspective, it's very clear that the economic benefits of climate change will be felt by the private sector, and the negative impacts will be borne by the public sector. And provided that people accept that that's the way things stand, I think that we can have a reasonable debate about whether or not it's an advantageous or a disadvantageous situation.
Would you like to add on?
Yeah, this could be a long debate, depending on where you stand. If you stand in Houston or Iqaluit, but the fact of the matter is, it's likely going to happen. So, we need to prepare for it and take advantage of it as much as we can. And so we can talk about mitigation, and that's a whole new story at a global scale. But I think the main thing is it's not necessarily also the new data and technology we need, is to get decision makers to actually listen and look at the data and start planning already for what's coming, whether it's the North Pole melting or other impacts of climate change and cryosphere in retreat.
You'd like to add?
No,
No, okay. Well, along the same lines, basically because this ice is melting and there is a Northwest Passage now, do you think this is a permanent change? Is basically the appearance of the Northwest Passage, of course, what you just mentioned as economic impacts, it also has national security implications. So can you comment on the permanency of the change, or?
I could speak to that a little bit. What I was trying to show in my presentation is that we have a range of forecasts for the future. But in the near term, in the next, say, 20 years, there's an incredible amount of climate variability, which means that we might have years where the Northwest Passage is open or where it's closed. And it will continue to be hard to plan around that. And the disappearance of the summertime sea ice won't necessarily make transport guaranteed each season. So I think the information that we're trying to provide to the public is critical in planning, and each year as we update the models and the forecasts, we'll be able to update that information.
But also, I know I showed a transit of Northwest Passage. It shouldn't be seen as a norm. It's really an exception. This is one of the most powerful icebreakers in the world, with a Canadian-owned and very short window of operation. It's not at all an economic viable route, except for these rare occasions still. You know, some of us that have crossed the Northwest Passage on powerful icebreakers have seen it's not an easy place to navigate, still very risky, even with decreasing ice, increasing flow of multi-year and ice hazards, poor charts. And on the economical side, it's not economical for long term. So short sea navigation will increase, getting minerals, getting resource out of the Arctic, in the Arctic. But as a transit route, like you said, either the Arctic Ocean or Northern Sea Route is a much better alternative than the Northwest Passage.
Thank you. On the science aspect, the question here is, what science exchange do you have with Russian colleagues? Russia is effectively is affected by sea ice change as well, and you can extend the question to all the Arctic countries, basically.
Some of the first ice that I looked at was the Russian Arctic. I worked at the Scott Polar Research Institute in the UK, looking at Severnaya Zemlya and Novaya Zemlya, and also some of the other smaller islands around there. And that was a very successful project because of the collaboration the team at SPRI had with Russian partners. And it is possible to get data out. There's not a national restriction on this. It's just a question of a translation issue. So, for example, Cryosat, the mission that I'm PI for, it turns out that an interferometric radar altimeter was flown by the Russians around Venus in the 1970s. Very, very similar instrument, and this is often the case. The ISAT sensor was a heritage of the Mars Orbiting Laser Altimeter, and you can often be narrowly focused on your own area and forget to look at advances that have been made in other areas. And of course, the Russian mission to Venus was very useful to know about sometime down the line when we had the full-scale mission to plan with Cryosat. There are access issues, but I think in my experience, it's just a language barrier and not a secrecy issue.
And yeah, I would say maybe talking more about on the ground, but in the scientific community, I would say is quite unaffected by the geopolitics at the higher level, at least at the university level. And even this summer, there's been a great expedition led by the Swedes on the Odin icebreaker across Russian shelf, involving all countries involved, from Canada also. And we have numerous exchanges like this by, you know, either having scientists come on our icebreakers or vice versa with the platform. Accessing Russian waters is not easy, but there are numerous ships and science icebreaker that do that every year. So there are collaborations at that level for sure.
Paul?
Similar story that just this summer we submitted a project proposal involving Scandinavian countries, Russia, and Canada and the US to the Belmont Forum in order to look at sea ice forecasting on subseasonal and seasonal timescales. So there's no question that the science requires full international cooperation.
Okay. Thank you for your thoughts. I guess the next question is probably something of the prediction. The question here is how much sea level rise is forecasted by, say, 2050? I think you had, well, pick a year and pick I think you've presented in your graphs. So I guess it's somebody that is interested in the 2050 range.
I will give a number, and my colleagues will correct me. It really depends. 2050, it's kind of a hinge on the effects of the forcings. But so I think, recalling what I showed for the end of the century, that it would be 30 to 40 centimeters, plus or minus, I don't know, 10 or 15 centimeters. That seemed to be the graphic I had up, which we could bring up again, I guess. But that's taken right from, I mean, what I really would say is I can refer the questioner who can approach us afterwards to the relevant information in the IPCC assessment. But I'd pass it to either of you to say a bit more about 2050.
I mean, sea level projections, particularly from the polar ice sheets, are a real challenge. It's very easy to predict how much ice will be lost from mountain glaciers. You just take a hairdryer and blow it at an ice cube. They will melt at a certain rate, and we know pretty accurately how much the temperature will change over the next century. Changes in the polar ice sheets are very, very different. The ice sheet models that we use today are not coupled into general circulation models, and so the behavior that we see on the polar ice sheets, rapid accelerations of flow, are not represented in the ice sheet model components of general circulation models. This is an acknowledged flaw in the sea level predictions, and so the jury has to be out on the amount of sea level rise over the next 50 or 100 years. What you can say from the observations, for example, in the case of Greenland, is the amount of ice being lost today is 5 times as much as it was 20 years ago. Nobody would take a 20-year record and extrapolate it into the future, but if one did that, the changes in sea level would be very, very different to the predictions of the models. And right now, the challenge is to develop ice sheet models which do represent the changes that we see in the satellite observations today.
Thank you. I have another question that basically we've talked about the science aspect, and you've talked about the tools that we need in order to have better data and continue to monitor and basically model the cryosphere. The question here pertains more on the link between that and I guess the human aspect, but do you think that, what do you think about the need to develop more and better communication systems? Basically, we've talked about the search and rescue capabilities or the transport that is going to go through that. So what are your thoughts about also the need to invest also in those kind of capabilities?
Well, again, it depends on priorities, but for sure, if you talk about search and it's not necessarily communications, it's actually investment in search and rescue, for example. So there are now, under Arctic Council, international agreements. The fact of the matter is Canada is a large place. Like I said, not a lot of people live in the Arctic, but it's still a huge issue when something happens. So whether it's this Clipper Adventurer, it took 2 days for the Amundsen to reach the ship. We had a helicopter accident last year, and the closest plane was closer to Tromsø, Northern Norway, than Trenton, Ontario, where they live. They lose from. So there is a huge logistical issue that would cost a huge amount of money, and I guess it's decision. We basically know what we would need to do. It's a political decision if it's worth doing it for, at least for Canada, as far as search and rescue in the north.
Okay, thank you very much. Any last thoughts before we close this session?
I just thank you for the opportunity to present our work to the audience, and I'm sure I speak for all the panel members, very happy to answer any questions afterwards that people might have that they didn't want to put to the panel right now.
Yes,
Paul?
thank you very much for the chance to speak with you this morning, and thanks for coming out.
And Martin?
Same here, I guess, but also this is a forum where we probably not normally talk about the human impacts of cryosphere, but it also shows that whether it's space observation, it's not only used by scientists, but it's now being much more accessible to even the Inuit hunter in a remote community that can access some products derived from space technology to help them in their daily lives. And that's progressed a lot, I guess, and make it much more accessible and much more usable by the common person, layman person.
You've just linked that to a lot of the application world, and like you say, not only science, not only modeling of the cryosphere, but also everybody that is being touched by by this. So I'd like once again to thank all of you for this very interesting tag team that you've been able to do. You've really met the challenge that we had put to you, and it's, I'm sure for me, I've learned quite a lot about the cryosphere and the importance of continuing to have effort and to use space, not only as we said, not only for the science aspect, but also in terms all the way to the user, the end user, and the impact on society itself. So thank you very much for your time. And yes, I do invite anybody that has a question that didn't have time to write it on a piece of paper to come right after this. And I'm sure, as you've mentioned, as you offered, they're willing to answer your questions one-on-one. So thank you very much. And once again, thank you